Okay, so now that we have our trig derivatives all memorized, all 6 of them, we're going to start using them. And we can combine them with all the other rules that we've already learned. So, from memory, we're going to take the derivatives of these functions. So, g of x is equal to x minus tangent x. First thing I notice is that there's 2 terms. I get excited because that's 2 problems in one. You can treat every single term as if it's its own problem. Does anything need to be rewritten? No. So here we go. We'll take the derivative of both sides. Remember, the left side is just as important as the right side. The derivative of g is g prime. The derivative of x is 1. And remember, that's like a minus 1 times tangent. So the constant rule says it could just be the derivative of tangent times negative 1. What's the derivative of tangent? Secant squared. Done. It's that easy. That's the derivative. Now, you also want to prepare yourself for possibly manipulating it into an equivalent answer in case this were a multiple choice, or maybe even if you wanted to use it later, a different version of that is a little bit more useful. So whenever you see a trig function that's squared, especially in the presence of a term that's a 1, your mind should be drifting towards what identity set? The PIDs. Yeah, let's review the PIDs real quick. These are the important ones that you need to know. Cosine squared plus sine squared is Papa PID. That's 1. If you divide everything through by cosine squared, you get 1 plus tangent squared equals secant squared. And so that's why I call that one baby PID number 1. If you divide everything through by sine squared, you get 1 plus cotangent squared equals cosecant squared. And that's baby PID number 2. You just have the cos in front. So using baby PID number 1, the middle one here, 1 minus secant squared could be equivalently written as what? Careful, not tangent squared, negative tangent. I'd have to bring it across the other side, right? This secant would come over here, and the tangent would have to go over there. Yeah. So it is equal to negative tangent squared. And that could be more desirable because it is only 1 term. But they are both equivalent. All right, next one. We got x times secant of x. X times secant of x. That's going to require the what rule? Product rule. This is the number 1 rule that students tend to make mistakes on. I like to put the parentheses. It just kind of helps each factor stand out more prominently. And if we have 2 factors, we're going to have how many terms? Not 4, just 2. As many terms as we have factors. So I like to take the derivative of the first factor first. But the left side is really what comes first, and that's either y prime or dy dx. So the derivative of x is 1 times, do we take the derivative of secant now? Do we do it now? Now? Do we do it now? No. No, we already took one derivative. So we rewrite it. Plus, now we rewrite x, and now in the second term, in the second factor, it's secant's turn. What is the derivative of secant? I like the secant x tangent x. Remember, when is the trig derivative going to be negative? When it starts with co. Yeah. So secant is just positive secant times positive tangent. Cosecant would be negative cosecant cotangent. And essentially, we're done. There's the derivative. Now, do you see anything that we can do with the 2 terms? Let's say later on we're going to set that equal to 0, which is what we do a lot of the times because we're trying to find horizontal tangents. Yeah, factor. We're not going to set it equal now to 0, but if we were, we would factor out a secant, and we're left with 1 plus x times tangent of x. And then from there, we could set each factor equal to 0. We can figure out where we have horizontal tangents. So either one of these are really correct. We always want to at least think about what we could do after we take the derivative in terms of simplifying. Does secant times tangent, does that simplify down to another trig function? Secant's like 1 over cosine, right? And tangent sine over cosine? So I guess we could call it sine over cosine squared, right? But I would argue that that's not any simpler looking because now we've created a fraction. But some of the things we can do with trig. Fun. Okay, differentiate each of the following functions and show that they have equivalent derivatives. Equivalent derivatives. If 2 functions have derivatives that are equal, do they have to be the same function? No, not necessarily. For instance, I have the graph of, or the equation sine of x. What's the derivative of sine of x? Cosine of x. What's another function whose derivative is cosine? How about, there you go, sine of x plus 1. The derivative of that is also cosine of x plus 0. So really, now you can see how you can create any equation whose derivative is cosine, right? It's always sine of x plus some constant. And what would that do graphically if you added or subtracted a number? What does it do graphically? It moves it up or down. So let's see why that works. It's always nice to have a graphical tie-in. If I look at this graph of sine, and I look at the slope of the graph right there, okay, what would happen if I moved that graph straight up or down? Would the slope of that line change at that same x value? No. The y values are very different, but the slope at that point doesn't change because even though the tangent line has a different y-intercept each and every time, what do we know about the slopes of those lines? They're the same because those lines are what allele? Parallel. There you go. So a vertical shift doesn't mess up the slopes. So you have two functions that differ by only a constant, they're going to have the same derivatives. All right, now it could be that they are the same function, right? With trig, there's all kinds of ways to disguise them. All right, so if we're going to take the derivative of this one, the first rule we're going to use is the quotient rule, the Hody-High rule. Good, I'm glad you're calling it the Hody-High rule. So here we go, f prime of x equals, let's switch to orange for Unity Day. Ho, and then d high. What's d high? Well, 1 goes to 0, but the negative cosine becomes positive sine of x. Good. Because cosine itself is a negative derivative. So there's ho d high minus high in parentheses, super important. D ho, what's d ho? Cosine. Good. All over ho ho or ho squared. So remember, if you're doing ho squared, how's that? Did you do it correctly in the bottom like that? Yeah. It's wrong, right? You either need parentheses like that, or of course you could do it like this. You could just write the squared in between the n and the x. It's a condensed version. So you're done with the calculus. It didn't really last that long, one line. But there is still some cleaning up to do. Sine times sine is sine squared. This right here, the next step, this is the most common mistake students make in the Hody-High rule. You have to distribute a negative from the left and d high from the right. So really we're distributing a negative cosine. So that becomes a negative cosine times 1, which is negative cosine. And a negative cosine times a negative cosine is a positive cosine squared. Yeah, all over sine squared. All right, here's where I see students get excited, and I understand the excitement in the math class. But you got to restrain it, because if you do that, is that correct? No. It looks like they should divide out, but they don't, because it's a factor in the bottom and it's only one of 3 terms in the top, so don't do that. But is there anything else in the numerator that we can still do? Yes, even though they're not written side by side, the associative property of addition tells us that we can associate these 2 terms, and we get sine squared plus cosine squared, which is, of course, 1. It's Papa Pid. So we're left with 1 minus cosine of x over sine squared of x. Now that looks right there like a decent place to stop, doesn't it? But can we keep going? Sure, we can keep going. There are 2 ways to keep going from here. One of the techniques that we'll be using throughout the year is the ability to split up terms in the numerator by putting it over the entire denominator. So I'm going to work from left to right here. We can call that 1 over sine squared minus cosine over sine squared, as long as you put them each over the entire denominator. Now, of course, what would that equal? Well, 1 over sine squared is cosecant squared. And cosine over sine squared. That's not equal to anything, but look what we can do. We can call that, we can split it up. We can call it 1 over sine times cosine over sine. Just kind of associate the factors like that. We did a lot of that with our trig limits, right? Verify in your mind that is the same, yes? Okay, now by doing that, we can use some identities, right? The reciprocal and ratio identities. What is 1 over sine? Cosecant. And cosine over sine is cotangent. So there's one way we can clean that up. Now, is that right here any prettier than 1 minus cosine over sine squared? It doesn't have the fraction, so some people might argue that it is prettier, but it does have the cosecant cotangent thing going on, which some people kind of have a distaste for. Does anyone see another way we can proceed on the left? Take out a cosine? Oh, yeah, from here, like coming back here if I work down. You said something about Papa Pid. We can call sine squared, we can call sine squared 1 minus cosine squared a la Papa Pid. Now, this is where it gets really dangerous if you don't know what you're doing. You might say, ooh, 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 ooh. The 1's divide out, the negatives divide out, the C's divide out, the O's divide out, the S's divide out, the X's divide out, and we're left with nothing over a floating 2. Right? Right? I mean, that looks like it should happen. But of course, that's not how it happens. It's fun to, say that. But there is something we can do. Because 1 minus cosine squared is a difference of 2 perfect squares, which means it'll factor into the product of 2 what you get? Conjugates. Okay, so it's going to factor into 1 minus cosine of x times 1 plus cosine of x. And that's kind of interesting because in the top we have 1 minus cosine of x. And now what happens? Yeah, now we can divide out those again if we want, and it leaves a 1 in the top. And lo and behold, we are left with 1 over 1 plus cosine of x. And that's pretty darn pretty. That's equivalent to that. What we're doing after the derivative is quite substantive, right? We're really doing a bunch of trig proofs, just manipulating these with trig identities and a little bit of algebra. Kind of fun, kind of good to review those. Any one of those could be an answer choice and a multiple choice, but of course any one of those could be something you prefer to work with. And if I'm going to be working with this, like by setting it equal to 0 or something, I'm liking that one a lot better. It's pretty small, concise. It has a fraction, but it has cosine, and cosine's kind of comforting, right? Maybe the CO in cosine is for comforting, right? We recognize him. We have a lot of experience with him. Cosecant, cotangent, not so much. I forgot what the question was asking us. It says differentiate the following and show that they have equivalent derivatives. Well, we have a lot of different versions of the derivative of this one that we can compare the derivative of the other one to, yeah? All right, let's come over here. G of x equals. Wait a minute. They're telling us that the derivative of this, which started off in terms of sine and cosine, is going to have the same derivative as this? I'm a skeptic. I need proof. Let's prove it. Do we need to rewrite anything on the right? We do? We could. I mean, there are certain identities that we can use, but there's 2 terms, and do we now know the derivative of both of those trig functions? Yes. So the left side becomes g prime of x. And here we go. The derivative of cosecant is negative cosecant times cotangent. Yeah. And then minus the derivative of cotangent is negative cosecant squared. So what happens when we have a negative times a negative? It becomes positive. So we have positive cosecant squared of x. Now, all we have to do is show that that is equivalent to the derivative of this. Well, we played around enough on the left side that I think that's going to be pretty easy to show, isn't it? All we have to do is commute the terms. G prime of x is equal to cosecant squared of x minus cosecant x cotangent of x. So remember, if we were doing this as a proof, we just showed that they were the same. You used to sign off on it, right? QED, something like that. Or you would sign your name. My favorite still to this day is sizzle. Right? It's hot, but it's sharp. All right, so those two functions ended up having the same derivative, which means they are either the same function or they only differ by some constant, and their graphs differ by a vertical shift. I'm wondering which one it is. You think they're the same? Probably. Let's see. If I start off with this one, 1 over cosecant is 1 over sine, minus cotangent is cosine over sine. What do I need to combine two fractions? A common denominator. Do I have one? I do. So I can put them both over sine, and I'm left with 1 minus cosine. Oh yeah, indeed, it was the same. But two very different ways to come up with an equivalent derivative. So the moral of this story is not only to show you that two functions can have the same derivative and yet still be different functions. If you are doing a question and it starts off in terms of cosine, if your answers are in terms of sine and cosine, keep going. But if you notice your answers are in terms of cosecant and cotangent, rather than do everything we did here on the left and then convert it to this cosecant, maybe it's easier just to split it up and say 1 over sine minus cosine over sine and get what we have g of x on b and then take the derivative. So looking at your answer choices and deciding where you want to go with your answer, sometimes just manipulating it before you start can save some work on the back end. An ounce of prevention is worth a pound of cure. And a bird in the hand is worth two in the bush, right? Okay. Yeah. And a stitch in time saves 9. You heard that one? A stitch in time saves 9. And don't drink downstream from the herd. All right. Higher order derivatives. We've already seen this with our calculus textbook that was thrown off the tower. Higher order derivatives just simply means take the derivative of a derivative. Or maybe take the derivative of that derivative. So we need a notation for it. This last one right here kind of ties up the relation among your three kinematic equations. Acceleration is the instantaneous rate of change of velocity, and the instantaneous velocity is the instantaneous rate of change of position. Or we can say that the second derivative, s double prime of position, is your acceleration. So we would call s double prime a higher order derivative because it's beyond just s prime. Well, we could keep going, right? We could take the derivative of the second derivative to get the third derivative, and we can take the derivative of the third derivative to get the fourth derivative. We can keep going. Some of those have meanings, some of them don't. But every time we take the derivative, we're talking about how the previous function is changing at that moment. So let's look at the notation. If we start with y, then the first derivative is y prime, second derivative is y double prime, third derivative is y triple prime. We use the prime notation. What do you think the fourth derivative is going to be? Like that? With 4 primes? Yeah, because if you start using tally marks, which those are really essentially, it starts getting kind of tedious, right? The fifth derivative would have to be that, kind of like you're playing dominoes, right? If you've ever played dominoes, that's how you keep score. Yeah, so we switch past triple prime to that. We use Arabic numbers, but we have to write them in parentheses. So if you just see y to the fourth of x, that is not the fourth derivative. That's the same as y of x, the whole function raised to the fourth power. So we put them in parentheses. And then in general, you have the nth derivative. It works the same with functions, f prime, f double prime, f triple prime, and then fourth derivative, fifth derivative after that with parentheses. Leibniz notation is kind of preferred, especially for higher order derivatives, because you're not messing around with parentheses at all. The first derivative of y is going to be dy dx, and we read that as the derivative of y with respect to x. Here's the second derivative. We go straight to the Arabic numbers. Now, if you look at that, it kind of looks like a typo, yeah? Like I put my squared in the wrong place, but it's not. We read that as the second derivative, that's d squared, the second derivative of y with respect to x. Now let me show you why it's kind of offset like that. If I start with my function y, I'm going to take the derivative of it with respect to x. That's the verb, right? That means the derivative of y with respect to x. When I do that, I just nestle the y up into the numerator and I get the noun dy dx. So that's why that notation is like that. To get to the second derivative then, I'm going to take the derivative with respect to x, the verb again, of my first derivative, which is the noun dy dx. And you end up with this right here. And so this should help explain why it's offset. Notice it's d dy. It's the derivative, and there's only one here on the outside, but there's one on the inside. So it's kind of like d squared y. If you were thinking about multiplying, d times y would be d squared y. And at the bottom, we have dx times dx, which would be dx quantity squared. We just don't put parentheses because we do treat the dx as a single unit. So that's why it's offset. What do you think the notation for the third derivative would be? D cubed y over dx cubed, right. And then the fourth derivative, d fourth y over dy fourth. So it's a little bit easier. You don't have to like switch from prime notation to parentheses. So in general, that would be the nth derivative of y with respect to x. All right, let's look at example 8. It says if y equals x cubed plus minus 5x squared plus 6x minus 4, find what the heck? What does that mean? The fifth derivative, yeah. It's not the function to the fifth power. And again, you'd have to be careful because if it just said find this, that's the same as the whole function raised to the fifth power. That would be like putting parentheses around here and raising it to the fifth power. And if you expected me to expand that, I'm going to show a little resistance because that's going to take a while, yeah? So, very important to understand what it's asking. It is the fifth derivative. Now, do you think we can go straight from the function to the fifth derivative? No. Our plan to find the fifth derivative is going to be to take the derivative of the fourth derivative, right? But how do we get the fourth derivative? Take the derivative of the third derivative. But we get the third derivative by taking the derivative of the second, and we get the second from the first, and we get the first from the function. So this is usually the case with the derivative. We have to generate the derivatives, we say, recursively. So in order to get the fifth one, we need all of the ones that come before that. We generate it recursively. So here we go. Working straight down, the derivative of y we call y prime, or dy dx. I'm going to use both notations. I'm going to expect you to be able to interpret and read both, but ultimately you can choose one. And now it's just the power rule, right? So we get 3x squared minus 10x plus 6. Sweet. Now we're into the higher order derivative land. To get the second derivative, we take the derivative of the first derivative. We call it y double prime. Or in Leibniz notation, d squared y over dx squared. Good. Remember, the left side is just as important as the right. So now we get 6x minus 10. We're on a roll now, right? Triple, y triple prime, d cubed y over dx cubed. We get 6. The fourth derivative, here's where it gets a little awkward. Y superscript parentheses 4, or d4y over dx to the fourth. And what is the derivative of 6? 0. Oh boy. What does that mean then for the fifth derivative? Also 0? How about the sixth derivative? 0. How about the 60th derivative? 0. 600? 0. 6,000? 0. 6 million? 0. Yeah, okay, good. So maybe in hindsight, we could have just jumped straight to the fifth derivative, huh? For this particular problem, but not in general. Notice that we first hit 0 on which derivative? The fourth. Now, with any polynomial function, if you continue taking higher order derivatives, you will eventually hit 0. You know why? Because the power rule by design says every time you take the derivative, do what with the degree? Subtract, make it one smaller. So it doesn't matter how big the derivative is or a polynomial, when you keep subtracting from a positive integer, you're going to hit 0. Now, it was a third degree polynomial, and we hit 0 on which derivative? Fourth. So, if I gave you a 50th degree polynomial, and I asked you to find the 51st derivative, would you have to go through and find all of them recursively? No, because on a 50th degree polynomial, you would expect to hit 0 when? On the 51st. Always one more derivative than the degree. That's nice. Now, if I ask you to find the 50th derivative or the 48th derivative, you would probably growl a little bit like Papa Bear did when he came home and found Goldilocks there. But I know y'all are good students, you would do it. But I'm also not a mean teacher, so I wouldn't have you do that. So if you have to find something that's an insanely high-order derivative, there's probably a clever way to do it, right? Right. Like, example, this one. Oh. Someone interpret that for me. Find the what derivative? The 447th derivative of what? Sine. You think it's going to be 0? You think it's going to hit 0? I don't know. You want to put D and E because you're in doubt? No. I guess the only way to get the answer is to start, right? The journey of 1,000 miles begins with the first step. Some say the journey of 1,000 miles begins with Dad refusing to ask for directions. Or Dad saying, I know a shortcut. Okay, I'm going to come off to the side here. I'm not going to use Leibniz notation the whole time. I'm just going to say y is equal to sine of x. Y prime then is equal to cosine of x. Easy. Y double prime is negative sine of x. Hey, we're on the second derivative, only 445 more to go. We might have to finish this for homework. Y triple prime. Positive or negative? Negative, because the negative goes along for the ride, and then the derivative of sine is cosine. Now, the fourth derivative. Positive sine, right? Because negative cosine changes to positive when cosine's derivative is negative. All right, and then the fifth derivative is cosine, and the sixth derivative is negative sine. Now I'm getting a deja vu feeling. The seventh derivative is negative cosine. And the eighth derivative is positive sine. And I feel like I'm going in circles at this point. Do you have that circular feeling? You should. Mathematicians, if they're nothing else, are pattern recognizers. We like to recognize patterns and come up with generalization and algorithms, shortcuts, if you will, to establish to get a desired result. I noticed that we started with sine, and I hit sine again over here on the fourth derivative. I hit sine again on the eighth derivative. I'm likely going to hit sine again on the 12th derivative. So every cycle of 4, it appears to be repeating. Is that true? Let's see. The first derivative then should be the same as the fifth derivative, and it is. The second derivative should be the same as the sixth. The third would be the same as the seventh. Yeah. So if it repeats itself every 4, there should be an easier way, right? All I got to do is see how many full cycles of 4 there are in 447. If I do that, I get to do some old school division. 4, 0, bring down the 4. 1, 4, 0, bring down the 7. 7, 1, 4, minus 3. Does 4 go into 3? No. So back in the day, you would put a decimal and a 0 and keep going, but this is what we're after. We're after the remainder. So what we're going to do is we're going to get back to sine 111 times. So if I do it 111 times, it brings me right back to here. All I got to do is do it how many more times now? 3. So if your remainder is 1, it's going to be equivalent to y prime. If your remainder is 2, it's going to be equivalent to y double prime. Our remainder was 3, it's equivalent to y triple prime. If your remainder is 4, you divided wrong. But if your remainder is 0, of course it's a function. So our remainder was what? 3. So it's negative cosine of x. There you go. We'll pick up with example 10 tomorrow.